OpenAI have done some interesting research recently with Codex, the language model for generating code. So I'm just going to review this recent paper they've released. So they recently, Microsoft and kind of GitHub have been looking at different language models. They created CodeBERT based on Roberta, which can do some kind of language modeling and kind of mass language modeling, so filling in a few missing parts of code, as well as just building a representation for code. It's probably used for code search at GitHub. They kind of took the representations both of comments and of code, and then they managed to fulfill some kind of odd searches where people describe a bit of code and use code as well in the search terms. There has been some other generators based on BERT too. So this is a lot of controversy around Codex. They're trained on all sorts of GitHub code that they scraped, so there was kind of issues with like secret keys coming out or code that is not necessarily MIT license or doesn't have a license. There's a lot of controversy. This paper just came out 2 days ago. They created this human eval project where it's just like a sandbox for running people's code. There's a bit of code in here that will kind of read in files and unit tests and compute this these. Yeah, it's got a few heuristics in here which will bail out if the program starts to do bad things and use too much memory and start doing system calls. So actually, we're executing people's code to try to pass tests. So there's a lot of speculation as to how general they can make the problem. OpenAI always likes to kind of strive for like general intelligence and not building in a lot of context, but for generating code, there's a lot of context you can use, like what kind of variables there are, what kind of imports, what your pip requirements files got in it. So they used a surprisingly small amount of context here. But you still, I think in future work, we'll probably need to use some more custom algorithms or AST building or the code running type traditional understanding methods to get to probably better results here. So this video is going around with it's doing a really good job on like top coder or leak code, hacker rank. So, and it looks like that they've specifically trained on these type of short singular method with some tests to get good at this type of stuff. So they kind of struggled with long docstrings. So predicting anything as you go further into the future is quite difficult. They found sometimes the docstring just wouldn't match up to the code, or it would not really describe the actual variables correctly. It's a big discussion at the end about got lucky because they were doing, well, they were very smart in using the semantics of code by actually running the unit tests and making sure it's functionally correct. And they can really do the same thing with generating docstrings. They just kind of did the classic log probability cross entropy type thing. found that the traditional kind of loss functions like blue, they kind of designed for language, and when they're trying to apply them to code, that they just weren't as successful as actually running the tests. It's kind of actual functional correctness. So it's quite interesting. They have asset one, meaning they go through and generate out the next word and do a full prediction, and then they see if the tests pass. And then they can do more of these. Sometimes later on in the paper, they'll be generating like lots and lots of different solutions, and then trying to rank them. And they said here that having a lot of doing a lot of samples, and then looking at across the whole sample, what's the mean probability. So if the probability of the whole generated sequence was quite high, then taking that as the best actually really improved the accuracy. And obviously actually running all of these solutions over the test suite is kind of much even better still. And managed to get pretty good. This is an ASAP K metric where we've got this GitHub project that will run lots of code in a sandbox, and it'll try to. It adds some kind of timeouts as well, like it won't run for longer than 3 seconds, and sees how many of your generated solutions are actually going to pass. So we're trying to use classic blue. They've got some graphs showing that it was just not didn't extend well to the programming language domain. So rather than trying to use some functional correctness instead of and so they kind of found that the bigger models kind of did a lot better. Kind of need a lot of predictive power to be able to predict this type of thing. So I've got some code for computing the top K. So how many of all of your generated results, how many of them are actually going to pass the tests? Put some NumPy code for that. So data collection is interesting. They went over 50 million public repositories, and they collected heaps of Python files, but they made sure the Python files were under a megabyte. They filtered out files which are likely machine generated. So if the lines are too long, or if there's not many English characters in there, then they end up filtering down a bit, so 50 gigabytes. We executed in this sandbox with containers. They found that starting with a language model, it didn't help, but it helped converge more quickly. So with a lot of language models, the tokens and the space is quite different. And when you start training, you can kind of quickly see a big jump, as there's inside the network, there'll be some of the weights will kind of know how to roughly recombine things in useful ways, but the actual input tokens will be quite mismatched with the meaning. I'm surprised that they didn't. They got away without doing much code-specific stuff. They did have a few more tokens, like the kind of a amount of whitespace token. There's a lot of inefficiency in coding whitespace. So they got some gains and use a few less tokens, and they generate until they generate one of these tokens, and that's kind of signaling the end of the method. Maybe that's a bit presumptuous. Some Python files do have, nested methods. Yeah. Maybe it's a bit more meaningful stuffing metric there. So this is kind of showing that they kind of really do need really big language models to solve this. Loss and how big the networks need to be in log scale, so it tends to get exponentially harder to get better results, which is same with the number of samples. That's log scale as well. So you have to, if you can keep generating lots of different samples and seeing if those pass the test, but then you're going to have to keep generating and generating lots and lots. If you've already generated, say, 100 samples, it's harder. Keep going. So I know it's not exponential, but probably not real. And they're finding kind of temperature they should use. So I did use they got a lot better results where you look at the average probability of the whole, like all your logits, so all of the probabilities of the words you're getting out, and then taking the result with the highest probability. Got a really good unit test pass rate. So when they looked at blue, it wasn't a very good indicator of if the tests are actually going to pass or fail, because it's kind of been designed for the natural language domain. It can really map well to functioning of the code. The code just looks kind of semantically, it sounds like Python code, but it's not functionally correct. That's the unit test. So yeah, if you generate more samples, you've got a better chance of passing. But the untrained models didn't do very well once they started training and training with bigger models. They're just getting better results. And if they use a huge model and use a lot of samples and test them, they can get a pretty good pass rate. So they have a network called Codex S where they fine-tuned it. They had competitive programming problems, and they actually scanned GitHub for projects which used either Tox or Travis CI. So they would actually run your integration tests through your code and then do some profiling. So they kind of need to, for their test harness, they need to boil it down into a unit test. So they literally just watch what's going in and out of your small function, and then they will generate it a unit test for your function, and then that can kind of go into the training data set. And they also got incorrect solutions as well to programming problems. Competitive programming domain, well-written problem statements and functions for test coverage. So, training data there. That's why it's obviously doing so well in these videos on those exact kind of problems. So there is a section in the bottom about how they can synthetically generate different kinds of problems by composing a few operations together, like get the next bit of the string or remove something from the string, and then they just chain all those operations together in a function, and then have a docstring that describes that chain of operations. Here, they actually filtered out hard examples so hard that they aren't going to learn something. Their algorithms are never really going to get the correct solution, and so they're just not good training examples. And they give a reason of why, which they theorize that some problems there's just randomness involved. So when they're creating their test harness, that maybe there's some randomness and their tests are actually not deterministic, or there's some side effects or stateful operations happening where it's just not easy to pass this this unit test and kind of get start getting information about like gradients and start learning something. So they're kind of too hard to be useful for learning. And that got filtering these out gave them better results on yeah, possibly. So Codex S, where they trained it on those two extra data sets, is better. And then the docstring generation is kind of a separate network. You can't use the actual unit test here, obviously. They can do some kind of a back translation. I'm not sure which language they translated it into and out of. assuming that's just a kind of a data augmentation that get used to keep generate a few different useful doc strings in different ways. Correct. It's interesting that it's not sample efficient to train. Also comparing it to human beings there. Computer science students can solve all sorts of problems. I did some interesting analysis of how many bugs there were. So if you kind of feed in some context with some bugs in the docs, and try to get the code out, then it does deteriorate the results. And there is a kind of similar bias. I call it kind of internet scale bias, where have issues with offensive associations. At the very bottom, they've got some showing that there's some issues with ASIC K, and that their code is doing an actual better job of numerically stably estimating it. A few of their example training set, and they've got these small procedure for how you would compose together some synthetic data. Just layering on top of these operations and describing the order of it. There's a section that kind of talks towards all the kind of really hard things to get right, like concurrency and parallels, and there's something that talks about imports, how you would actually suggest what kind of importing to do. Often it's not taking into account like the project level context, like requirements.txt. Yeah, with the imports, probably the most scandalous part of the paper is they're suggesting that it's suggested TensorFlow 6 times, PyTorch 3 times, and they find that the two libraries are rough substitutes of each other.